So I thought it would be fun to put together a quick video on the reactions of benzene, because we look at benzene ring reactions when we're doing the two-step reaction. So anyway, benzene is of course the typical hexagonal molecule that people really tend to associate with organic chemistry. And indeed, there's a funny little meme, things I learned in organic chemistry, interest in reactions, nomenclature, i.e. naming stuff, deadly compounds, and then how to draw hexagons. So there's a hexagon of benzene, C6H6. Now I could have drawn this benzene this way, or I could have drawn it that way. And if you notice the difference between them, you've got starting at 12 o'clock, you either go clockwise starting with a double bond, or you go clockwise starting with a single bond, and then just draw the alternating single and double bonds as you go round. So two possible structures for a hexagon of C6H6, and indeed Kekulé, the chap who came up with the cyclic structure of benzene, thought that it did exist in these two molecular forms and that they were in equilibrium with each other. Now if that was the case, then when chemists were able to look at structures using X-ray diffraction or electron diffraction, what they would have expected to see are alternating long and short bonds, because a carbon-carbon single bond is about 154 picometers, a carbon-carbon double bond about 130 picometers. So benzene, you would see 154 next to 130, next to 154, next to 130, and so on. To probably nobody's real surprised by the point that they discovered it, when they got to look at the structure of benzene, they found that every single bond length, every single carbon-carbon bond length was equal at about 139 picometers. So in other words, each of these bonds the same and longer than a double bond, so in other words weaker than a double bond, but shorter than a single bond, so stronger than a single bond. So the best way to draw that was a hexagon of this whole single bonds with another little hexagon made up of dashed lines indicating that each bond is more than a single bond but not quite a double bond. Now how does one explain this? Well, what one does is one says that it's not equilibrium that relates these structures, but it is resonance. Reality is not this structure or this structure. Reality is the average of the two possible resonance structures. And so, of course, the very familiar way to draw benzene, we could draw it like this with all of these dot, dot, dot lines, but the other way to draw it is to put a circle inside it. So this is a way that a lot of organic chemists don't really like to draw benzene, just the idea that you have every single bond is the same, more than a single bond, not quite a double bond. So essentially benzene doesn't behave like it has alternating double and single bonds. It behaves like it's got all equal kind of 1.5 bonds. Now let's try and explain that and visualize what that means by refreshing ourselves on pi bonds. Okay, in a normal double bond you have carbon here, whatever its things are going off, maybe hydrogens. You've got a bond that's just the two orbitals pointing straight at each other. But then you have these p orbitals on each of the carbon atom that's going to be bonded that are pointing up and down from the molecular plane and interacting with each other like that to make a pi bond. Okay. Now this determines the reactivity of this carbon-carbon double bond, because here you got lots and lots and lots of electrons here, and of course electrons attract positive things, and so positive things can come in and attack that carbon-carbon double bond to make a so-called addition reaction. Okay, this pi bond here is very susceptible to attack. It's sticking above and below the plane of the molecule, ready for things to come on in, grab some electrons, make bonds, and so on. Okay, now if we think of benzene, well, each of the carbons has got one of those p orbitals sticking up and down out of the plane. So if we drew it as our alternating double and single bonds, you'd have a pi bond here, for example, and then single bond, and then a pi bond here, and then a single bond, and then the back a pi bond, and then a single bond. Or, of course, you could have a single bond here, and it'd be these two that are pi bonded, and then a single bond, and it was these two that are pi bonded. So in other words, because of that delocalization of the electron density through the double bonds, what were the alternating single and double bonds but are now 1.5 bonds, we say that these p orbitals, instead of being localized between two atoms, they're now delocalized over the whole molecule. And this delocalization gives that particular extra stability. These are not electrons waiting here to be attacked like they are in the alkene. These are electrons delocalized out in a nice stable fashion. So what that means is that benzene doesn't do addition reactions. You take a benzene ring, and I'll draw it here with this alternating double and single bonds, and you react it up with the same type of reagent here. It doesn't add by breaking a bond. What it does is it substitutes. One of the positive bit, which we'll say is like the X here, attacks and bonds to the ring, kicking out a hydrogen, which then hangs out with the remaining Y. So addition reactions for carbon-carbon double bonds, substitution reactions for the benzene ring, because the benzene ring is not really alternating single and double bonds. It's that whole delocalized bond all the way around the ring. Now, you need to know the reactions of benzene, so I'm going to go through them rather quickly. There are 5 important ones that you need to really know for your A-level, plus possibly a 6th that I'll leave it up to your teachers to tell you. But if you take a benzene ring, one of the most straightforward reactions is you can react it with a halogen, chlorine or bromine, to put either a chloride or a bromide atom by substitution. Reaction that we do in the 2-step, react up a benzene ring, or a compound containing a benzene ring, with nitric acid and sulfuric acid, and that nitrates the benzene ring. If we just had sulfuric acid in there together with some SO3, this is fuming, really nasty sulfuric acid that I don't think you play with much in school, then it will put on this sulfonate group, so that's a sulfonation reaction. You can make carbon-carbon double bonds with these substitution reactions via so-called Friedel-Crafts reactions, in which you take either an alkyl halide or an RC double bond OCl, so I would call this an acid chloride or an acyl chloride, and you just put on the non-chloride bit on the molecule. So you can see here you put R on there, the rest of the molecule other than the chloride or the halide, and here you put on this C double bond O, and then C going to an R as well. That was the other bit of the acid chloride. Both of these are Friedel-Crafts reactions. This one is called an alkylation, and this one is called an acylation. And you can learn fun things about those reactions and all the distinguishing features when you get into university chemistry. It's always fun, I believe, to think about mechanisms a little bit. So let's spend the rest of this time applying some mechanistic perspectives to these reactions. Now, the electron ring, of course, which is what we have in a benzene molecule, and that is the dominant feature of a benzene, is of course negative. And what do negatives love? They love positives. And so therefore the attacking group is going to be positive. And we call the attacking group an electrophile because it loves phile, electrons, electro. In other words, our attacking group here, when we're trying to explain the reactions of benzene, the attacking group has to be something positive. Now, there's ways we can generate those positives. For example, the easiest one is think about chlorine coming up. We're thinking chlorine's not very positive, is it? But you might have noticed it's not just chlorine, it was chlorine with a catalyst in there, in particular, in this case, AlCl3. Now, the aluminium in AlCl3, if you just draw the structure out with it being an aluminium bonded to 3 chlorines, is rather electron deficient. And it's even more electron deficient. It's only got 6 electrons because it's got 3 bonds, but of course chlorine, nice and electronegative, is going to be sucking electron density away from that aluminium. So it is going to be ripe for attack by the lone pair on a chlorine atom in a Cl2 molecule. So you get this kind of species here. Essentially, the lone pair on the chlorine gets attracted to the aluminium, so there it is coming there. Now, because this is an electron pair leaving the chlorine to some extent, it leaves the chlorine a little bit positive, and because it's coming to the aluminium starts having more electron density, and we think of it as being slightly negative. Okay, now the result of that is that, of course, this chlorine's losing some of its electron density to the aluminium, so says to its chlorine friend over here, hey, how about I have a little bit more electron density from our bond, which means that this chlorine starts becoming a little bit positive. So can you see where we're going here? We've got something sticking on the end of this complex that's a little bit positive. So enter our benzene ring, enter our weird complex with a little positive end, and this little positive chlorine says to the lone pair, or the electrons in the benzene ring, you're electrons, I'm slightly positive, you like me, and so we draw a little curly arrow. Curly arrow, remember, is just to show the direction in which electrons are going in our proposed mechanism. Extra electron density from the benzene ring, we show it just for simplicity's sake as being some localized on this double bond here. Electron density going from the benzene ring to the chlorine, making a sort of bond there. So when we get that, then the chlorine says, well, I'm getting electron density from the benzene ring. I'm getting a bond here, so there it is, making the bond between the carbon of the benzene ring and this chlorine. And you've got this AlCl3 with an extra chlorine anion floating around the place. Okay, now notice this here, right? This, you could call it an intermediate. I like to just call it a little structure there that we're trying to sort of explain a mechanism with. What's happened is that you've got two electrons going from this bond. If you think of it just in a localized double bond, two electrons going, leaving therefore this carbon and this carbon. Well, this carbon's fine because actually both those electrons are going to making a bond to the chlorine. So this carbon bonds to the chlorine, still has the hydrogen to which it was bonded. This carbon, on the other hand, has lost its part of that double bond without anything to make up for it, so it's a little bit positive. So remember this structure here, because we're going to get even more detailed with it shortly. The idea that first of all, when your positive bit attacks the benzene ring, you get a 4-coordinate carbon that is next to a carbon that has a positive charge on it. Okay, double bond has left this carbon, been used by this carbon to make that extra bond, thus this carbon is positive. Now to continue on with this mechanism here, this point, this chlorine here has some electrons, and it says to the hydrogen, hey, how would you like some electrons? And the hydrogen says, well, that would be okay, but I'm actually bonded to this carbon. And the chlorine says, well, just tell that carbon to go away. So the electrons in this bond between the carbon and the hydrogen go off to compensate for this poor little positive carbon there. So we draw that like that. These electrons moving from here to making a new bond here. And there is our new structure with the substituted chlorine coming in. And of course you've made the HCl here, the H from the benzene with the remaining Cl from Cl2, and you got back your AlCl3 catalyst. Another fun one that we do in the two-step reaction is nitration. You take sulfuric acid and nitric acid. Now, we always think of sulfuric acid as being a strong acid, and nitric acid has been a strong acid. Sulfuric acid is actually a stronger acid than nitric acid. So it is in equilibrium in which the H2SO4 has given an H to the HNO3. The H2SO4 having given a proton is left behind with its conjugate base, HSO4-, and you have the conjugate acid of nitric acid in which the HNO3 has gained an H+. Now it's this particular species here that we're interested in. It looks like this. There's the original nitrate, NO3. Original nitric acid would have been the N, double bond O, O here, and then an O and an H. And then we protonated that oxygen there. Okay, now at this point you have water, and water is a wonderful leaving group if it could leave. And so you get some movement of electrons, right? The nitrogen doesn't want the oxygen to leave because it's sharing bonds with the oxygen. So this oxygen here, that of course has an extra charge on it, uses that extra charge to make a bond with the nitrogen, at which point the nitrogen says, oh, okay, I've now got 2, 4, 6, 8 electrons, I'm happy. So it's quite happy to let the oxygen of the water take the 2 electrons in that bond there. So I have a little curly arrow there. The water leaves, breaking this bond, the electrons go to that positive, and the nitrogen now has got a fourth bond, not to the oxygen that's leaving as part of the water, but to this oxygen here that's sharing its negative charge with it. So we make this species. That's the water, don't care about the water. There is this NO2 that is positive group that can attack. Then it's just the same old thing. That's the benzene ring. Here's the positive coming in. 2 electrons go from how we're drawing a localized bond on the benzene ring to make a bond to that nitrogen. Right, like that. And of course, again, those 2 electrons were bonding between this carbon and this carbon. This carbon's still good. It's making a bond to the NO2 group. This carbon, on the other hand, is positive. So there's that intermediate structure again, where the first part of a substitution is getting a 4-coordinate carbon next to a positive. Okay. Anyway, then water, remember this water up here comes on up, says to that hydrogen, why don't you come with me? So you get H3O plus, okay, an acid, which of course was what we started the whole thing in the first place, with the NO2 substituted. So there's some nice fun little mechanisms.